Thank you for coming. I'd like to read an acknowledgement that we are on Treaty 6 territory, the traditional lands of the Cree, Saulteaux, Blackfoot, Nakota Sioux, Dene, and Métis people. As researchers and artists in the field of neuroscience, we recognize the long-standing wisdom Indigenous people have cultivated in understanding the mind, body, and spirit as interconnected. Indigenous knowledge systems and healing practices offer profound insights into mental health, neuroscience, and resilience, and the neurobiological impacts of trauma, which are now echoed in modern neuroscience. We're committed to honoring and learning from Indigenous perspectives on wellness, and we seek to engage in respectful and collaborative partnership to further understanding and healing for all. We pay our respects to the elders, knowledge keepers, and generations of Indigenous people who have lived in harmony with this land. And we're grateful for their resilience and stewardship, which continues to inspire us as we strive for a better understanding of the human brain and mind. Well, the Neuroscience and Mental Health Institute is a novel initiative in the University of Alberta. It's a collective of people that are interested in furthering understanding, research, understanding how the nervous system works. The goal is to find better treatments and through that understanding for neurological and mental health conditions. And I think we have a really nice night organized for you. This event is connected to Connections, which is an art and neuroscience display at the Royal Alberta Museum. And I hope you'll all have a chance to visit. It's open until June. So I think there's some beautiful works of art depicting that important connection between neuroscience, mental health, and art. Tonight, it's the art and science of brain rhythms, which is an interesting facet of all of the work that NMHI does. And you're going to hear some absolutely wonderful talks. And I think it's very timely because there are arguments out there that rhythmic and dynamic activity in neuroscience might be more important even than gene expression, right from algae all the way to societies. So rhythms are inherent in everything we do and we know about it. You're going to hear a lot about it tonight. So some great talks coming up. I'm going to turn it over to the moderator of the event, Dr. Janette Mailo. So thank you again for coming.
Thank you all for coming. Welcome to the first in a series of public lectures that are focused on the art and science of investigating the beauty of the brain and the mind. My name is Janette Mailo. I'm a neuroscientist here at the University of Alberta, and I will be your host for the evening. So first, a little introduction to sort of what we're here about today. As a young scientist, I was really drawn to the field of neuroscience because of the beauty and the complexity of the brain. At its most basic, I think our skull is basically filled with this gray, mushy material that is filled with 86 billion cells that connect to one another with electrical activity. But it's really the sort of connection or collection of that electrical activity that forms every single thought, every emotion, every experience you've ever had. That activity is what drives how we love, who we love. It holds the collection of all of the memories we've had over our entire lifespan. And it fundamentally creates the experience of our mind. And so really how the brain is able to transform that electrical activity into that incredibly rich experience of being is really one of the great mysteries of our modern age. So I find myself very fortunate as a neuroscientist interested in these questions to have landed in Edmonton. Because the Neuroscience and Mental Health Institute here at the University of Alberta is one of the leading brain research institutes, and it is home to hundreds of scientists and clinicians and trainees that have really devoted their life to understanding these complex mysteries of the brain in an effort to really generate and create better therapies for diseases of our brain and mind. And I think that our current age is a really exciting time to be able to ask these questions because we're living in this time where we have this incredible technical advances with advances in human imaging, gene editing, as well as machine learning. It really puts us at this forefront at being able to answer these sort of complex questions around the brain. And yet, despite the fact that scientists are making these incredible advancements in understanding how the brain works, there will always be this threshold where knowledge fails us. And it is really that gulf between our academic understanding of how the brain works and then our also inherent knowledge of what our mind is really where science stops and art steps in. And it's really art that can serve as an expression of ideas and thoughts where otherwise words would fail us. It can act as a mirror to help elicit reflection and introspection. And it also can inspire new perspectives and new ideas. And while art and science are often thought of as sort of the polar opposites of the academic spectrum, I would argue that it's really through the blending of art and science that we get the closest to the truth. And so that's really been the mission here at the Neuroscience and Mental Health Institute for the last 5 years or so. And it's about bringing the arts and humanities and sciences together in order to forge new connections and insights into the understanding of the brain. And so this initiative was really spearheaded by my colleague, Janette Mailo, who's a neuroscientist here at the NMHI, along with her colleague, Marilyn Oliver, who is our videographer tonight. She is a professor in the art and design in the Faculty of Arts. And together they have curated this exceptional exhibition, as you heard from Doug, which features artwork and scientific images that portray aspects of neuroscience, brain disease, and mental health. This exhibition is called Connections. It's currently on display at the Royal Alberta Museum until June, and I really encourage you to check it out if you haven't already. And so it's really as part of this exhibit that we've also organized a series of public lectures. And so before we get into, here we go. Before we get into today's talk, I wanted to really make a plug for the next talk, which will be called The Art and Science of Addiction, held in later this spring. Tickets will be released closer to the date, and you can check back at the website for more information. It will be updated soon. I also wanted to make a shameless plug for donations. It's really important for us at the NMHI to make sure that these events are as open and as accessible to our community as possible. So we keep them free. But the reality is we really get very little support to be able to host these events. So if you like this event tonight and you would like more of them, I encourage you to make a donation if you can. I have made a link to the donation page here. This takes you directly to the NMHI donation page. All donations go directly to the NMHI. You can also find this link in your program tonight or also on our website. All right, so tonight, brain rhythms. So tonight's lecture is on the art and science of brain rhythms, and it's really based on the idea that the fundamental unit of information in the brain is not how individual cells behave, but rather the pattern of activity of populations of neurons across the brain. So to put it another way, it's not about the individual notes of the brain, but rather the music that emerges from those notes that actually encodes our conscious experience. So today we're very fortunate to have an artist, 2 scientists, and a clinician who are here to share their wisdom and experience on rhythms. So first up, we have a local award-winning sound artist, Gary James Joynes, who will share with us a clip of his immersive visual sound presentation called Sonic Suns. And he'll also share his reflections on how rhythms may influence brain and mind. After that, we'll have Clayton Dickson, who's a professor here at the NMHI, who will discuss why brain rhythms are not just important while we're awake, but also play really important functions when we're sleeping. After that, we have a talk by Mathewson, another NMHI scientist who uses brain rhythms to better understand everyday activities like cycling and gaming. And then finally, Janette Mailo will wrap up the talks. She's a pediatric neurologist here at the University of Alberta, and she will share with us how she uses brain rhythms to understand and diagnose brain diseases in the smallest of patients. And so we will have these series of talks sort of back to back, and then following that we will have a moderated discussion on stage, and we will be able to take questions from the audience. So please ask that you hold your questions until the end of the lecture to the discussion portion of the evening, and very much looking forward to an engaging discussion with all of the speakers. So with that, my introductions are over. I will pass the stage first to Gary.
Hello, my name is Gary James Joynes. I'm a local sound artist here. I've been working for many years in music. I started as a rock and roll. If you can imagine, my hair is very short now, but there was a time when my hair was much longer, I can assure you. And for years I traveled across Canada playing in bands, and I was a lead singer and a bass player in some heavy metal bands. And just, I guess musicians can be kind of flaky. I'm putting that out there. So around the age of 30, after my last band kind of fell apart, I was really driven to keep creating and trying to do creative activity. But I was heartbroken because my band broke up, and I'm now like 33 years old. I felt like I was kind of running out of time. And then something wonderful happened. The universe delivered the idea of deep listening and ambient music. And simultaneously over the one summer, I was introduced to the likes of Bjork's music, Brian Eno's music, and Tortoise, post-rock kind of bands. This was way out of my wheelhouse of what I was listening to for my whole life. And the common denominator that I realized in all this music was this thing called a synthesizer. So I bought my first synthesizer and started playing with it, and I was like, oh my goodness, this is a sound color machine. I looked at my bass that I'd explored for almost 20 years, and I'm like, I love you, but I'm gonna hang you up for a while. And I started playing with synthesizers. And I've been working as a graphic designer and as an art director for years too, so I was always interested in the connection of visual to sound. And I was creating in a genre called live cinema. And I was touring around and doing festivals, doing live audiovisual performances. I was creating my own abstract visuals and sound work, very deep in your body kind of sound work. And I guess it would have been about 2007, I was introduced to this film by a Swiss scientist named Hans Jenny, and he coined the term cymatics. And cymatics is now something that we're seeing a lot of on YouTube, people playing with the Schlage plates. I'll get into all that a little bit later. But I was blown away that there was a science, an analog science, that you could explore by vibrating particles, very, very simple kind of experiment. And you would see a direct connection between the sound and visual. They were fused. And I was like, oh my goodness, I gotta see what I can do here with this. So I built my first what's called a wave driver machine based on a 350-year-old experiment called the Schlage plate. And I dove in. And it's been about 17 years now that I've been playing in this field, and there's been numerous different types of projects that I've done with it, all of which I'll kind of take you through a little bit as I go through my body of work. But ending up until last year, I created my most recent installation. It was called Sonic Suns. Now this was an exploration of a number of different things. It was the idea of putting sound wave energy through light, and I was using liquids. So I created a cymatics water tank, and essentially sending cones in there, and learned over the course of about a year of playing with this machine to mine an enormous library of various animations, I guess. These are all not in the sense of computer. None of the stuff that you see here tonight was done with any kind of CGI at all. This is a core analog kind of experiments that I'm playing with, and then I'm using digital tools to kind of to present them. So when I was talking to Anna about what she would like me to present tonight, she had asked me to present a little bit of my Sonic Suns installation. So we're going to start about an 8-minute excerpt section of Sonic Suns, and then we'll move on from that. I can talk a little bit more about what's going on after that. But thank you very much, and I hope you enjoy it. Thank you. This is Sonic Suns. Hertz. So that's kind of fun to watch, eh? Yeah, I was constantly being blown away by what I was discovering as I put my synthesizers in tune, and this sense of wonder that I was constantly discovering all these new amazing things that I could find with this experiment. So what you were witnessing there was an installation called Sonic Sun that I presented last year at Peter Robertson Gallery. And it had, I'll show you some photos of the actual installation, because there's a whole other element that we don't get to see with this. But what we were hearing there was a series of frequencies that Nikola Tesla came up with. And when I discovered that, it kind of blew my mind. And as I researched more into it, I discovered that Tesla was very interested in numbers, and specifically very interested in the numbers 3, 6, and 9. And the relationship of the number 9 was something very important and dear to his heart. He did a lot of work and thought a lot about that. So much so, and I don't know how he did this, but with a mind like his, who knows, he came up with this thing called the toroidal harmonic resonance circle, or the arc. And it consists of those, I was calling out the frequency numbers as the tones were coming up. So they're all related to number 9. The first one being 180 hertz, 1 plus 8 equals 9. 270, 2 plus 7 equals 9. 360, 450, 540, and 630. And he postulated that if you sit inside those tones for a good amount of time, that it will have healing properties on the body. That was very interesting to me. It's like, wow, that's quite a claim. And then when I brought up the frequencies on my synthesizers and built the system, I actually built a 6-channel sound system where I could sit and test this theory that he postulated. And what I found happening after, I sat in there for almost a year meditating and experimenting with myself, and I would find often that it would put me in a mild psychedelic state, almost like a low dose of LSD. I was like, wow, this is quite something, that these specific frequencies can have this connection on our brain and actually move chemicals around in such a way. He took it even further than that. He claimed that by sitting at these frequencies, it would open your pineal gland and cleanse your third eye and open you to the spiritual realm. And I'm not sure if I can prove that. But I can tell you my own personal experience has been quite profound, living and actively living with these tones. So much so, almost of the compositions that I've been doing for the last year are simply using those 6 frequencies and variations in composition. I'm just going to move on to the slide portion here now. Here we go again. Okay. So for the past, like I said, I discovered the science of somatics about 17 years ago after seeing this film that was made in the late 60s, early 70s by this Swiss scientist named Hans Janette. And he coined the term cymatics, which is the science of visual sound. And again, using analog experiments of creating different types of machines and various experiments. So cymatics basically is a Greek meaning wave, and like I said, it's Hans Janette is the guy who coined this term. He was actually playing and going even further back. His influences went back to about 350 years to another scientist, a German scientist named Ernst Clayton. But if you go even further back, there was a guy named Robert Hooke, who was the first guy who discovered nodal patterns. And I don't know if you've seen the experiment that's on YouTube quite a bit now, where you've got a metal plate and you put sand or some kind of particulate on it, draw a violin bow. And what's actually happening is you're getting a resonance, which is a self-amplification of that tone, and it'll actually have enough wave energy to push the particles and draw these incredible patterns. So I was like, wow, I'm going to see if I can do something with this, because I was blown away by the idea of an analog way to create a whole visual library and bring that into my live performance and then later into a gallery environment. And all of this, I'm trying to imagine everything that's going on in my brain while I'm doing all this kind of stuff, because this conversation that we're having tonight is really focusing on that. I'm not sure if one thing I was talking about with some of the scientists in the back room before we came out was, would there be a way that I could bring some of these frequencies and tones and we could actually measure them and actually see what's actually happening? So that's sort of a question I have to the scientists in the room. Again, these are pictures of me using the clavy plate, or what I call the wave driver. There's a little bit of a history of Hans Jenny. I said, like, the guy who coined the term. He did this wonderful film, like I said, that totally inspired pretty much the whole direction of my art practice for the last 15 years. And the idea is you're creating a machine, setting frequencies. It usually works best with pure sine tones. And because there's no harmonics, it's this essentially the purest form of a sound wave that you can get, the sine wave shape. And I'm amplifying that through this machine. It's an incredibly violent activity. To get enough wave energy, you can imagine with the sound wave to actually push particles, it has to be pretty loud. I can assure you I've blown many speakers over the years doing this experiment, and it voids your warranty, by the way. So it was shortly after the experience of being introduced to this film, I was hanging out with some artists at the BAM Center, and I'd previously done a few performances there, and the director of the BAM Center pulled me aside after one of my performances. Gary, really interested in and very moved by your work, and please keep in touch with me whenever you're in Bath. Please come and see me. I want to hear what you're thinking about and what you're working on. So this was right after I saw that film. I ended up at the Bath Center jamming with some dancers and media artists, and I remembered this invitation for coffee. So I called her up and I went and we had coffee. She's like, "Gary, what are you thinking about these days?" And I'm like, "Oh my God, I saw this film and it completely blew my mind. I want to do an installation and I want to build this machine." And I just kind of went off on it. She was just like, "Wow, this sounds fantastic. I would like to offer you a research residency." And this is me being naive to the whole kind of art world. And I'm like, okay. I didn't even really know what that meant. I went back and was jamming with some of these artists, and they were like, "Oh, how was your afternoon?" I'm like, "I don't know, I was just offered a research residency." And they were like, "Holy shit. Like, that's actually usually a jury thing, Gary. It's not something that's usually handed out over coffee." And I'm like, "Oh, great." So, I went back, and for 6 months, they gave me this studio in the side of the mountain where I could be super loud and blow up a whole bunch of speakers and really learn. This is a picture of the set that I have there. So again, I was talking about the synthesizer earlier, and as things evolved with the synthesizer, I fell in love with what's called the modular synthesizer, which is what I'm using to make all of this art. All the visual art that you see was created on machines like this. And these machines are, I would say it's like surgical control over analog sound. You program with all the cables, you create all your own sound circuits, and you have this unbelievably fine and subtle and control over what you're doing with the sound after you kind of figure out how they work, which took quite a few years. But anyway, I feel pretty confident with it now, thankfully. So moving on, I have a long history of a live audiovisual performance. So I started doing performances using the visual aspects of the somatics. Somebody that had the pleasure of presenting at some major festivals like Mutech and Electra in Montreal. This is me at Electra. Just thinking of the massivest sound systems and screens, and like as a young kid coming up playing in rock bands, it's pretty wonderful to get to play with those kind of toys when you're a little older, let me tell you. So moving on, I started getting ideas about sound installations. The first one I did, again, was this piece called 12 Tones. This was a series of 12 frequencies where I meticulously drew all the frequencies through the cymatics plate, and I developed this drawing vocabulary where I can very slowly build these up. You've probably by now seen on YouTube where lots of people are running these machines and they blast the frequency and it's magic. It's just like, whoa, it draws the pattern. As an artist, I was like, okay, that's cool, but could you actually learn how to finesse and really make high quality art out of it and really learn how to draw a sound? That was the question I had. And for many years, I've been working with that, and thankfully, I think I got pretty good at it. These are some of the images, sort of close-up resolution of some of the images that I've released over the years. This is, for example, this is a higher frequency. You can see there's a little bit more information happening. This is a lower frequency. The wave is bigger. You've got more energy to actually create the relief. And I could play with shadow work, like in the bottom of the circle. Another one, this was amazing. I remember this moment because for some reason I had this, the plate was running, it's screaming at me. Particles are jumping, like when you're running a machine, that sound is jumping like, inches off the plate. And for some reason I just had this intuitive moment and I cranked the volume even more. The sound flew up in the air, and then it landed, and then I shut the sound off, and it created this unbelievable kind of burst of all those extra particles. I'm like, man, this is the gift that keeps on giving. And it was a whole other way of drawing. So I just kept pushing and into this experiment and seeing what I could do with it. When something wonderful happened after that 12 Tones installation went out, there was a lot of press that went out nationally. And I got contacted by the curator at the Cawthorne Centre in Toronto. She said, Gary, are you suggesting that sound wave frequencies look like secret Mandela patterns? And I'm like, certain specific frequencies absolutely do. She goes, well, I'm curating a show of artists that are exploring the sacred Mandela patterns, and I'd like you to create a piece for that. So moving on, I created this piece called Ouroboros, which you may have seen at Louis Blanche in 2015 in City Hall. I had the opportunity, and I have to say, this is a proud moment for me, being someone who's not a super sports guy. But I had 17,000 people through this exhibition. That's more than an Oilers playoff game. Go hard. Again, look at this. Very clearly the 4-nodal kind of thing that we see in recognizing Mandela patterns. Again, all frequency, all tone, all pure tone. But this is actually essentially what's happening in the invisible world. The sound moves through us, around us. It's a physical wave. It's just invisible. The wonderful thing about cymatics is it enables us to actually visualize what's actually happening. From there, I got the idea of, okay, wouldn't it be wonderful to capture that genesis moment of the sound being created from nothing? And I created this work called Sound Bursting, which is an installation where you actually saw very fast introductions of these tones and I created a sound composition that moved through time. And then from there, some of the other discoveries, there's a series I did called topographic sound, where I started recognizing almost like land or geographics or topographic kind of images. And some certain frequencies I discovered, one in particular, 2.57 kilohertz, would literally have a standing wave that would turn the sound or the sound movement into a liquid. It would flow like liquid. In fact, if you see at the very bottom, all the little fine lines here. Here's a grain of sand. And these were grains of sand that were following the leader. And because it's such a violent experiment, it would turn the sand to dust. And that's what you're seeing, the sort of fine gradient dust. And as I would detune the oscillator, it would leave an echo of where it was. And I'm like, my goodness, this is a whole new mark-making drawing technique using sound. So I explored that in that series. These are a number of images that came up from that series. As I mentioned earlier, I've blown a lot of speakers over the years, and I was actually curious what was going on behind the scenes as I was destroying all these. So I mined into looking at inside the speaker, it's called a voice coil, which is a coil of wire that's connected into a magnet, and you've got that polarity that's moving up and down. And essentially, when a speaker blows, the wire breaks and it just goes silent. And over the course of a number of years, I had this library of blown speakers. Thankfully, I didn't throw them out. And I looked at them, and some of those speakers that died very early were still almost perfectly golden copper. And there was this range of gradation over how badly they were destroyed, up to the point of like completely mangled. And I'm like, this is so interesting. I could basically tell a life cycle story here where we start as these perfect unscarred beings, as babies. We move through life, we have experience, we have scarring, and then eventually the wire breaks. I'm like, wow, that could actually be an idea for a very interesting art show. So this was a piece that I did called Broken Sound, which won the Foot Award in 2016, which I'm very proud of. That's one of the things that I discovered there, which leads to what we're coming back to the sonic suns idea, was as I projected these beams through thin particulate fog, I recognized that, what we see in nature, crepuscular rays that we see if we're walking in the forest and there's a mist and that wonderful light that comes, the shards of light that shoot through the trees. Or you see it in clouds sometimes where there's mist and you see these unbelievably, they're essentially called God rays, they're referred to. I'm like, my goodness, wouldn't it? And then I was sitting there watching this installation of my own work and like looking up at these going, okay, how can I figure out how to put sound wave energy through light? That was the next question I had. So that was sort of what inspired that, was this piece. Thus, we come to 2013, and after about almost 3 years of work, I presented this installation called Sonic Suns, which I showed a bit of an excerpt of the raw material that's inside of that. Now, when I was creating those animations, I was thinking about the beauty that's inside the actual animations that you saw, which are quite stunning to watch. As I was tuning and animating my synthesizer, the whole idea was to create sound movement that I could control. It was essentially a liquid tank that I built that you see there. And there's a speaker underneath. I'm using that modular synthesizer that's on the left. So I'm sending frequencies to the liquid and developing this vocabulary of how I could move it. But the whole time I was thinking about, I want to move the liquid to deliver the movement through sound through light. And I knew in theory that every point of reflection in the liquid that I actually have control over that reflection in the water, would draw a line through space, through fog, and thus I would have the ability to control the sound wave through space visually, through light. So that was the idea for this one. Again, right here, what if these rays could be an actual visualization of sound wave energy movement through light? And that was the genesis idea, or the moment for this piece. The thing I was talking about a little bit earlier was Nikola Tesla's influence in this. And again, you can see at the bottom of this, the frequency range, the toroidal harmonic energy activation resonance circle, which that's a lot. That's pretty cool, right? You say that, like just. This is Tesla's mind coming up with all this. And again, so interesting that these numbers work so simply. That summation of those two numbers related to the number 9, but then that translates into this whole other world in our brain and what's going on. And to the point of, like I described earlier, the healing properties and just these magical things that were happening to people in the installation. So yeah, I'm just gonna, this is it pretty much. I wanted to thank you very much for the opportunity to present my work, and hopefully this sets a nice stage for the wonderful science that we're going to hear about now as we explore the brain. Thank you very much for having me today.
So thank you, Gary. That was absolutely fascinating. My name is Clayton Dickson. I am the I'm nothing now. I'm the director of the Brain Rhythms Lab, so I'm actually very fortunate to have been invited to this. It's kind of like a symposium on brain rhythms. One of the things that Anna said during her introduction was one of the things that I was going to speak about. The idea that by studying brain rhythms, what you're actually studying are the collective activation and sequential activation of the subpopulations of cells that you can record from at particular locations in the brain. And of course, that activation gets transmitted to other cells and basically influences it in a very rhythmic fashion. And so there's an allegory here to music, which is basically that what the brain is creating is virtually a cerebral symphony. And so it's that cerebral symphony that we study in the Brain Rhythms Lab in order to understand how the brain is coming about doing these various activities. Really what I'm interested in is all of the spontaneous activity that occurs, when you think the brain should be resting. So in other words, when it's asleep. And the fact is the brain never stops functioning. And as my wife, who's also a neuroscientist, likes to remind me, the brain is really there for one essential rhythm, and that's to make sure you keep breathing. So anyway, I study the cerebral rhythms, which is just another kind of esoteric rhythm, I guess, in her books. So one of the things that I should tell you about myself is that, like Gary, I used to be a rock musician as well. Although I've been told that as a drummer, I'm not actually a musician, I just hang out with musicians. But it's certainly the case that the art of percussion certainly influenced what I decided to do as a career, which was to become a professor. Although I did, like Gary, have an opportunity to potentially be a rock star. What I found out becoming a professor is that really it's the same thing. So, just going to tell you a little bit about what the brain does to set the tone. What does it do? Well, it's an input-output device. Basically, you feed it a stimulus and it emits a response. And it uses electricity to do so. And we can record that electricity. But essentially, in this model, it's a sensory motor integrator. Basically, it takes sensation in and it selects a motor response. But it doesn't always give you the same response. The brain can learn, so it's modifiable. It can also store that information. And most importantly, to us, is that it has these two different types of states, online as well as offline. So during sleep, it's not responsive to the environment. You're not creating behavior unless you have to make a postural change. But essentially, it's generating its own activity spontaneously. So it's this kind of activity that's interesting. But most importantly, the brain is a rhythm generator. So it not only generates the breathing rhythm, but it also generates all of these activities that we can record from the cortical surface and also other structures inside the brain. So as a psychologist, I have to argue with my colleagues all the time because they consider sleep to be one of the most uninteresting behaviors that you could ever study. To look at it, you might agree. The fact is that when you're looking at the brain, it's actually really fascinating because it goes through a number of different states that are physiologically regulated. So basically, there is some physiological push to create sleep and to maintain it. If you don't get enough sleep, you get very unhealthy. And all animals sleep. In fact, some animals sleep together. And basically for us, it's creating in the brain this internally generated set of very interesting patterns that can also switch between different kinds of states that show the coordination of neurons in our brain. And really importantly to us, sleep may function to lock in particular types of memories, especially different types of states in the brain. So I'm going to tell you about a structure, my special brain structure, the one that I love the most, the hippocampus. Hippocampus means seahorse, but as you can see in the rat, it doesn't look like a seahorse at all. It's that blue structure within a rat head, and you can see the brain. That blue structure was more like a cashew, actually. So whatever the Greek word for cashew is would have been probably more accurate. But basically, this structure is really important for encoding a particular type of memories that are known as episodic. So basically, the episodes that we have within our life. So personal events, memory for personal events. Rats can also show episodic memory. And as you probably figured out, rats are our model for studying sleep. They're really, really convenient because it turns out that they're nocturnal. So it means that while they sleep, we can be awake. And we're usually awake during the day, so it's actually really good. Studying humans means that you're going to be sleep deprived. So, does sleep actually enhance episodic memory in rats? Well, this is a study that was conducted by a number of students who are all listed here. What we did is we used a particular task called a circular water maze. And what you do is you hide a platform in this big pool of water, and you ask the rat, okay, can you find the platform? Eventually they find the platform. It's hidden, and what they have to use is they have to use all of the features of the room that they're in order to figure out where that is the next time you put them in the pool. You drop them from different places, they look first, they see where they are, they figure out where the platform is, they swim directly to it. So they learn this really fast. So we teach them over 8 trials or so, and then we give them a break for about an hour. And what we do in that break, that delay, is we tell them to run, or we tell them to broom, or we just tell them to do nothing, just go to sleep. And then we ask the question, okay, once we come back from that delay, what is their recall like for where they just learned in terms of the platform? And we can run this day after day after day and give them a different platform location on every day so that we can really test their episode from that day. What's the point? It turns out that yes, sleep does actually benefit their performance. So anything that's low on this graph means that they swing very quickly to the platform location. So they've remembered it really well. In the sleep group, out of all of these groups, the ones that were grooming, the ones that were exploring and running around were the best. So that looks like sleep is really good. So what the heck is happening in the hippocampus during all of these states? Well, there's very different patterns of rhythmic activity that can occur. So during exploration or even during REM sleep, you see this rhythm that's around 4 hertz and upwards up to about 10 hertz. During sleep, it's usually on the low end, but it's rhythmic, but it's fast. During grooming, what you see is really a regular activity. It doesn't look like a rhythm is being generated at all. In fact, they're usually fast rhythms. During slow wave sleep, however, what we see, is a very slow pattern. It's about 1 hertz or 1 cycle per second type of rhythm. So why might slow waves be important? Because we think that it's the slow waves during slow wave sleep that are really helping with these types of memory. Well, it turns out that across the cortex, you have very good coordination of these slow rhythms. So if we make recordings from these 2 red arrow locations that are in the cortex that are very far apart, you can see that the rhythm from both of these in red, again, on the other side, are very, very similar. Whereas if we record from the hippocampus, we can still see a slow rhythm there, but it's a little less coordinated with the cortical region. And so these green arrows signify times at which the cortical slow oscillation is very well coordinated. And you can see that in the red, those same ones are actually not that well coordinated with the hippocampus. So there are times when we can coordinate and times when we discoordinate, and this could be really important for the types of processes that are fundamental for actually modifying synaptic connections, the connections between neurons, in order so that they can form and strengthen a memory. Now, one of the other things that's really interesting about this type of slow activity is that even though it looks very similar across these single cortical regions, what we can also do is we can also record from these regions using optical methods. So this is a recording that my former PhD student Anastasia Greenberg did in the lab of Majid Mohajeroni at the University of Lethbridge. So they collaborated on this project, not just to record slow waves, but also to see if we could alter them by applying electric fields to them at specific frequencies, much like the examples that Gary gave you before. And so one of the things that you can probably see is that they don't look the same for every cycle. So everything that's coming out in red is actually neural excitation. Everything that's in blue tends to be the opposite. So, voltages that are less excitatory. So what you can see is that the brain, even when it's effectively asleep, is performing all of these complex things. So not only do we get these traveling waves at slow frequencies, it turns out that the slow frequency itself helps to organize local activity. So what it's doing is it's creating frames of activity and non-activity. So those sort of hot colors in that last map versus the blue colors. And so during those hot colors, what's happening is that neural activity is actually engaged. So you get these frames of activity that happen, and that activity helps to shape the kinds of oscillations that are being created by networks of neurons within that region. So there's these 2 gamma traces, and if you look at where those are the highest, they basically demonstrate the same kind of relationship to this slow filtered activity that Anastasia looked at. So that same kind of organization of neural activity happens as well in the hippocampus. So we were really interested to understand, okay, how do these two very disparate regions, cortical regions like frontal regions and the hippocampus, actually coordinate? And so this is where my former PhD student Brandon Howard comes in, and my current PhD student Mitchell Prosody, who is in the audience, come in. So they're basically interested in understanding how those regions connect. So one of the things that Mitchell is going to be looking at is whether or not this interface that's well known between cortical regions like the prefrontal cortex, a very long way away from the hippocampus, could probably have cortical-cortical connections all through the cortical mantle to finally reach this other beautiful region, the entorhinal cortex, which is the source of all information that comes from the cortex to the hippocampus. So, does this play a role? Brandon's task was actually to look at another region that's a shortcut. Basically, the prefrontal region sends input to a thalamic nucleus known as the reunions nucleus, or RE in this diagram. And so, what Brandon did was a number of very elegant experiments to show that basically those thalamic neurons did show clock-like activity at slow frequencies that was transmitted to the hippocampus, and when we inactivated that region, it completely disrupted the coordination between the medial prefrontal cortex and the hippocampus. So basically, the punchline is that the reunions looks like it's very important to couple memory areas. So now, Mitchell's task in the next few years or so is going to be to figure out what role the entorhinal cortex actually plays in this, and whether or not the reunions has an interplay together with those things. So Mitch is going to be very busy in all of this stuff, but just last week, he wasn't busy enough, obviously. He came to me and said, "So Clay, have you ever really thought about making music with brainwaves?" So kind of the opposite thing, what Gary is doing is trying to understand how these tones might influence brain activity. So I said, yes, I've always thought about that. And, I've had a couple of ideas, but I just never made it happen because I have really bad programming skills. Mitch had very good programming skills. So he set about creating music from brainwaves, which is actually an example of a cerebral symphony. And Anna, I have no idea where that might be, if it is on your computer, and whether or not it's even going to play. It's a monster file. Nope. No worries. I'll play it for the next time we have a brain rhythms connections. Okay. So how do I get back to your... So I'm a PC person, not a Mac person. That's why I don't understand the interface at all. So, anyway, what essentially Mitch did is he actually took all of these different frequency bands that are really important in terms of brain activity and show rhythmicity that can be organized by slower rhythms. He broke them up and created triggers for them, and then applied different voices to musical tones to those particular frames, and created this, recreated, I guess, this cerebral symphony so that we could actually hear it. And I have to agree with him. After you play it a number of times, you start to recognize themes that come up. So it's actually a nice mechanism to understand different types of rhythmic patterns. So what have I told you? So sleep is this really active period for the brain. It demonstrates a number of rhythms, different types of rhythms for different states, and so presumably different types of function that are ongoing when the brain is in those different states. Sleep benefits memory, so basically slow wave sleep seems to benefit these hippocampal dependent episodic type of memories. And slow waves can be coordinated across very vast regions of the brain, not just the cortical mantle, but also between cortical structures that are important for episodic memory as well, and the hippocampus itself. Slow wave coordination occurs through the Reunion's nucleus, and of course it helps to organize those faster rhythms as well. So by studying sleep as well as memory processes, we hope to be able to understand better how these work in both in intact brains, but also in terms of brains that are subject to disease states. And we hope that by understanding them better, we'll be able to improve the lot for those who might have deficiencies in terms of memory in those brain operations. So again, I would like to thank Anna for inviting all of us to do this, for setting up this very nice lecture. I'd also like to thank all of my colleagues at the Neuroscience and Mental Health Institute, as well as all of my students who helped to do this. Thanks also to the sources of funding, but mostly to all the students who do all the work. I get to take all the glory, and they sit in the audience.
Thank you for coming. Thank you for clapping. It's a great example of a rhythm that you all just generated somehow together in synchrony, using your brains, listening to each other beside you and synchronizing your rhythms. I want to also thank you for coming here. I have not spoken to adult humans very much for a year. And it's so fantastic to see you all here and to listen to me and my colleagues speak. I'm also really excited to come out of the closet today because, not in the way that you might think, I secretly have been an artist this whole time, not a scientist, and I can't really tell anyone, but this seems like the perfect crowd. So you'll see from my talk today, I'm going to diverge a little bit from maybe the program and talk about some of the art that I do as well. But I think the same can be said for other scientists. We all wear different hats and masks. And thank you to the NMHI Museums and Anna and Doug for having us. This is what the EEG research looked like when I was in graduate school. And if I was here to tell you about this, you would probably go home and be bored. It's almost as boring as you could get doing brain research and rhythms. And I don't want to tell you about that. I want to tell you about the progression of this kind of technology towards today and towards the future. So here is on the top left is Hans Berger, who discovered EEG in 1914. Didn't publish it for 10 years because he was secretly studying it in private because he was actually studying telepathy. And he finally convinced people after a decade that it was real, and it got taken up. And one guy that went to study with him there next is Donald Lindsley, who took it back to America, where he started the first EEG lab, where he taught Manuel Donchen, who had that kind of system when he retired that would sit on your table like that. And Manuel Donchen's student, Monica Fabiani, was my graduate advisor. And that is not Frankie, that's Jackie, who's here too, who's now 12, turning 12. And they look very similar, but that's him with an early prototype of a portable EEG system. And I want to show you how the EEG hardware has transformed. And I think you can see, based off this difference in form factor, how many opportunities this change is going to create. So as we moved out of the laboratory, when I moved back to Edmonton to start my professorship, we took advantage of all these miniaturized electronics and portable phones that we all have to miniaturize our laboratory. So now you can try to record data from your watch or from your phone. You can even get really tiny computers that run off batteries and laptops. And we created an EEG laboratory that we could use on a bicycle. So we spent 7 years studying people's brains as they biked around Edmonton, and we developed a system that worked and even translated it into a partnership with some industry partners that were trying to study how different types of road affect our attention. So in addition to this kind of miniaturization of our laboratory, I've also taken advantage of this miniaturization of technology to bring the teaching of EEG to more individuals. First, with this kind of setup where we have 4 portable EEG systems that are made by a company in Toronto called Interaxon. They're sold at Best Buy as like a meditation practice, and they're $100 or $200, as opposed to the $20,000 system in the backpack there. And so at that scale, we can have 4 different computers and have a laboratory component of a class, for example, where students learn to program. In the course of our studies, one really big advantage that we had of doing these outdoor experiments is that we could record, instead of in the exact same boring room doing different games, we could record doing a variety of different things, the exact same data, and then compare across different experiments. Here's an example of our alpha power, 10 times a second activity was different. And this is with a student of mine, Joanna Scanlon, who's spearheaded much of this research. Before any of this occurred, when I was very young, my Aunt Wendy was in a car accident on the way to Jasper and suffered a fracture of her skull that left her in a coma for a year. And she had to relearn how to talk and to walk. And so my whole childhood was, I was confronted with this situation of someone with an injured brain. And it was really what drove me to become a neuroscientist. And when my daughter was born, who's not here, Rosie, because she's too cool to come to watch her dad talk, even though her piano teacher came, and that if I would have known, then I probably could have got her to come. When Rosie was a baby, Wendy was over at her house, and she was watching Rosie, and we were so excited because it was a perfect kind of situation for Wendy and for Rosie. They all seemed so happy, but as Wendy came upstairs to leave, she was not speaking. And Claire Skavutza, my wife, who's a professor in the psychology department as well, which is why we don't have any other third parent who's not a professor to watch Frankie right now. And Wendy appeared to be having a seizure. She couldn't talk and she couldn't express to us what was wrong. And we said, no, it's okay. Maybe you should sit down for a second. And she was a lot like me, very focused on what she wanted to do and didn't really mind that we were telling her not to do anything, and just left and got in her car and wouldn't listen. Drove and hit the side of the road, or just kind of crashed her car. And she lost her license for the 3rd time that day, and maybe began a spiral down of deterioration for the first time in my life that I saw, as opposed to what I was seeing before, which was an improvement. And so, at the time, I, in my house, even had this kind of Muse system that I showed you back here on the table, and I had just been using it that morning. And at this time, I'm also, not to speak very highly of myself, but I'm a leading EEG researcher in town. And of anyone to have a seizure at their house, I'm the right guy, right? You'd think. And I was so demoralizing to not be the right guy after all the work I had already done to get to become a neuroscientist and to be the person that she could best use at that moment, to not have the tool that I needed right in that moment. Because this system, even though it looks nice, still, you have to open up the computer and you have to like open up the terminal like you're hacking and start typing in. Oh, I'm not on the right screen. You have to like hack your way in. And so in an emergency, it's not really going to be the right solution. I realized that day it was very hard, but what it did for me is it really drastically changed the trajectory of my research again. And instead of trying to do more laboratory-like studies that better replicated things people are doing, I just started building more things because they could be more helpful. I couldn't help her with any of the 30 papers I had published by then, that's for sure. So I just wanted to start making more useful things. And luckily at that time was this explosion of different companies that were making portable EEG systems for consumers, because it's a more difficult entry to get it to medical patients, but the consumer market's an easier market to break into. So there's sleep aids and meditation aids, all sorts of different interesting technologies. So a student of mine, for example, Daniel, took a lot of these Muse headbands to Malawi, to a remote village where they're studying longitudinal changes in the brain activity of young children in the village. And I could tell you a bunch of intermediary stuff, but this shows, I think, how drastically different this is compared to like helicoptering in that chamber to record an EEG. Not only can you do this in the desert in Malawi, but you can get 50 of these devices into a classroom at once. So Interaxon sponsored the U of A by sending us a box of 50 headsets to use in the classroom, as long as we did a press release. I think that was the deal. I brokered. And then we got to send them this nice picture that they could use, that these are 50 different students learning in pairs, live with their own brainwaves about how brainwaves work and how they could run experiments using brain activity to test different theories that they have. Around this time, I also collaborated with my brother Corey to create a toolbox to analyze brainwaves using these new, exciting deep learning models that kind of hit the market a couple of years ago that have now taken off. And this toolbox is a really well-used toolbox. I've never published it or gotten credit from it really for anyone, except I think I'm helping a lot of people because hundreds of people are using this. When we were in Toronto presenting that paper, that toolbox at a conference, my wife Claire and I stumbled across this laboratory across from the art gallery that you might have seen on Dundas. It says Man Lab or Fun Train or iCatch or some funny engineering word like that. This is the laboratory and studio and home of Dr. Steve Mann, who I should have put a picture right there, but I'll jump ahead to his picture, really? Yeah, there. Dr. Steve Mann. And Dr. Steve Mann is an inventor and a professor at the University of Toronto, and he had a group of young undergraduate and high school students that were running the most unbelievable experiment I had ever even heard someone propose at the time. Just as I walked in the door, and they said, "Oh, you came to the right place." And this is what they were doing. They were having EEG headband on people, and then they were trying to move, for instance, in this image, move lights back and forth across the field of the person's view, and the lights were flickering at a frequency that the brain can pick up, like say at 10 hertz. So when you hear a 10 hertz sound or a 20 hertz sound, your brain resonates at that same frequency. They measure that frequency in the brain waves, and then they illuminate the light depending on how strong the brain activity is. And so the parts of the image where you see light are parts of the image where this individual was attending to at the time, because the more you attend, the more your brain picks up that rhythm. And what you can see on the top and bottom is that you can actually visualize like the cyclops gaze of his attention. Here it's very focused in this area here, here in the top, he had a wider aperture in what he was open to in the world. And that blew my mind. And they've continued on and made these amazing images like this one that showed him attending to the Coca-Cola can, which was flickering at a certain frequency, where they can illuminate kind of the rays of light that are bouncing into his eyes. This was the first experience for me to bring us back to art of how a scientist could use art to show what they were thinking, to show what they were finding. And that the art was in fact more important than what was written in the paper, because this is what people are seeing, especially people that you present to outside of the expertise that you're studying. And so that was so crazy to me that I said, okay, well, I'm going to stay in Toronto for another week and try something wild. Let's make a picture from people's brain activity, an actual image of what they're looking at. What if we had people trace on the screen with their eyes? So instead of saying, look here, we say, look here, then look here, then look here, then look here. Like, slowly move your eyes across like an old TV, but much slower. And we flicker the word no at a frequency that their brain picks up. And then every pixel of the image that we create after, every circle, is a place where they looked. We use an eye tracker to see where they were looking. And when they look at the letters, we see a slightly bigger response in their brain to that frequency. This looks pretty grainy and terrible to you and I, but so did the first pictures of atoms. I was watching a video on Barry Savian last night. That was the first one. Look at what we did within a month. We were recreating real shapes. So those are real shapes that were hanging in the lab flickering. And we could recreate the image that people were seeing. At the limit, it looks like we could get resolution almost good enough to like maybe tell two people apart. Now, keep in mind, we've really cheated here, right? This is why a neuroscientist might not have done this project, because it's not really a natural behavior to scan your eye across an image like this. So much so that we had to avoid the security guards at this next part of our experiment, where we decided that even though the Art Gallery of Ontario didn't allow cameras in, we could probably capture a picture of the art. You can see we were cheating and have a camera we're recording with behind. But here's Jeremy Stairs, who now works at Divergence Neuro in Toronto, and he's staring at this art piece by Vilja Clemens, and her art was, it was such a good exhibit. This is my idea, because the exhibit was called To Fix an Image in Memory. Am I done? No. Okay, this is good. And we did. We stole the art. We had people go around town with one of these devices, and we could even track, based off what they were looking, if it responded more to the flicker of the lenses in front of them, we could indicate that they would likely remember those things better, and then we gave a memory test, and in fact they remember things better, that they have better attentional cueing to. I was hoping to get to show you more of this, but I will leave it at this. I'll just conclude quickly. But to teach the class with the EEG headsets, I've created this website that you can go to, that you can use a mock data, or you can get one of these headsets like I have around my neck, and you can connect your headset to this site and learn all about brainwaves. But you can also make art with the brainwaves. Here's an example of one where I create like a group of little robots floating around. I created another class called Neuro Art, fit into this lecture, and in this class, which was during COVID, I had to drive the 50 EEG headsets around. Students all made their own interactive brainwave control art project using another website that you can go to online. So it can connect to this kind of headset, and it can make visual or auditory representations of your brainwaves. My colleagues and I also make newer electrodes, like I alluded to earlier in the talk. So we make portable, flexible electronics that can shrink and conform to the body. We accidentally even once electroplated our skin. And because we're scientists, not just artists, we went and tested it in an animal model, and it did work, in fact. I'm going to stop there and say that I've gone and worked with a number of companies to try to commercialize these products because we ultimately want to get to be able to help people. We have one of these in an ambulance right now that goes out to people that gets a stroke, and it immediately records some time of their brain activity, and we're able to predict the stroke severity based off just 3-minute recordings of this simple EEG device. So here's another paper we're just publishing with Brian Buck and Sibby and Mahesh and Cassandra Wilkinson, who went to medical school where we're looking at strokes. So here's again the development. I think I can only imagine what the next 10 spots on this chart are going to look like. This is going to lead really nicely into the next talk about babies. There's just going to be baby sounds the whole time. Thank you so much to all of you, and thank you for your patience, and thank you for coming.
Inviting me. My name is Janette Mailo. I'm a pediatric neurologist here at Story. So I'll show you how we use brain regions in care of our sick babies and children. My pediatric neurologist, but my main work is in neonatal ICU and pediatric ICU with critical care. So I'll show you mostly examples from there. So how are the brain regions created? I think you've already seen. So for us as neurologists, essentially, for us, this is the difference between normal and abnormal activity. And normal activity is essentially normal coordination and normal communication between nerve cells, the neurons. And normal activities, and I'll show you some of the EEG examples that we use. And normal activity is just calm activity between nerve cells going from one cell to another, and there is some product, it means that we're doing something. Abnormal activity is this usually actually either there's lack of activity, but for us, especially in pediatric neurology, dealing with sick children, it's actually this excessive activity. And you might think lots of activity is a good thing, not necessarily, because in our world it leads to seizure. So in my world, when we are evaluating brain rhythms, the big thing is the stage or the context. Like what are we talking about? What is the setting? What is the context? When we are talking about brain rhythms and the whole drama of evaluating brain rhythms. So for me as a neurologist, the age is very important because the brain rhythms that are normal in a newborn are not necessarily normal in a 4-year-old or 18-year-old. Is the child awake, is asleep, somewhere in between, or is it some abnormal state, for example, we cannot arouse them. So the other part of the context or stage is, are there any illnesses? Are there medications on board? Substances? So this is what kind of my work looks like. Most of the kids I see are brought in by the ambulance. This is our pediatric ICU and the neonatal ICU. So the interesting thing of brain rhythms in my work is while and for those who have been in the hospital and saw somebody sick, friend or relative, you've probably seen that we have those big screens where we're measuring oxygenation, rate of breathing, rate of the heart rate, blood pressure, but we have very little direct information about brain function. That's one thing that is kind of a black box. It's very difficult for us to know what the brain is doing, especially in a sick child. So this is what we use. This is the EEG or electroencephalogram, this fancy name is for the machine that measures the electrical activity of the brain, the connections, how quickly the brain cells communicate or how slowly. So we're using the one that says, the normal, that's like loads of electrodes on the head. We can use the simplified ones, which are easier to put on, easier to read. I don't know, missing part of the brain covered, so everything is plus and minus. This is what we do, these are the simplified, there's 4 of them, or we put tons of electrodes. It depends if we have somebody, it depends on the setting, again, stage and setting, the context. So this is a good and a really bad. So those we don't necessarily need the EEG machine for, because if somebody is normal and awake, you can actually figure it out. Talking to them, examining them. Normal sleep again, somebody looks like they're sleeping, they're awake, you don't really worry about that. You can see how sleep, the waves are much slower.
So each of those kind of vertical lines, the dark ones, is 1 second. So the number of waves in between those 1 second is much slower. The normal sleep reading is good, much faster. The other one, normal awake. Those are good. We're still not reading the EEG for those. This is a complete lack of brain region, which is really bad, but we don't necessarily need the EEG for that because we can figure it out by checking the patient. This is what we actually need a machine for. Because this is what we cannot figure out very often, especially in a sick child. We really need a machine. We need something. We need the EEG system to tell us what is the brain doing. Because very often, especially in a sick child, and the younger they are, and more so, we actually cannot tell if they're having seizure. And the seizure is the bad thing that can happen between in the brain, between the cells that are not communicating normally. So once we know the seizure, we know what to do. We just need to know that there is a seizure in a sick child. And that's why we need the EEG machine. We use the bigger one, that's the very simple one that we use mostly in very young children. But it's very, very helpful because we can help the brain or can help the sick child once we know what's going on. So this is actually one of my little patients. They started. The parents very kindly agreed that I can show this in these videos. This is the baby. You might think this baby is just stretching. It kind of looks like it's just stretching, but if you have this video. And the baby doesn't go a lot of them until you treat it down. This baby is perfectly normal, developing 100% like any other normal baby, so it's doing fantastically well. But we needed that information to know that those were seizures so we can treat it and protect the brain. So that's why the brain waves help us. They help us monitor the brain, they help us to know what's going on so we can actually help the critically ill children and babies to stay healthy and to actually treat whatever disease is affecting the brain, mostly the seizure. Because if you don't know that the seizures are occurring, which we often don't, without the electroencephalogram or the measuring of the brain rhythm tools, then we don't know the seizures are occurring. And if you're not treating seizures, actually the seizures become a big problem. It might be too late if you don't know. So those are the rhythms. I showed you the normal. This is everything in between. So the first one, just an example. Coma, you see how very slow the brain rhythms are and not very coordinated. There's a coma, and some people get better, some people don't. So we kind of need to know what's going on to help them and try to treat what we can. This is another one which is quite abnormal. This is what there is no activity, there is some abnormal activity, no activity, not very good rhythm, but still maybe we can help if you know what's going on. This is also one of the bad brain dysfunction that we sometimes see in children, the very abnormal. You can see, if you remember what the normal rhythm kind of calm waves look like, this is not very calm, this is something that is not right, this looks very chaotic, not good. This one is surprisingly doesn't look good. This is one of those that something is really going on, not good, but the background rhythm is actually good. So this is a child that you can actually have a normal interaction with while the brain is firing at a very abnormal pace and something really bad is going on at the same time. So it's one of those very strange rhythms. But again, we need to know, because some of those you wouldn't be able to tell by just examining the teaching. So this is another one, and I'll show you that abnormal rhythm also makes abnormal movement and our body acting abnormally. So this was a child that was very sick after a very serious accident, severe brain injury. So this twitching is very abnormal, so corresponds with a very abnormal activity in the brain. Again, for these ones, my eyes, you can just tell that something's wrong, but it's good to see the rhythm so we can try to do something. So I showed you the abnormal rhythm. I told you that it's suppression, and then activity and suppression again is very abnormal. So in neurology, nothing is simple. It can actually be normal sometimes. So in a very, very young child, this is a totally normal rhythm. So we can show you somebody older is very abnormal in a young child, and somebody very, very born very early at 24 weeks. This is absolutely normal. And sometimes it can be normal if we do that. Sometimes we have a sick child that we need to introduce this kind of rhythm to protect the brain, just to almost like reset the brain. So it's kind of, would it be normal? Well, maybe not normal, but it's something expected, something that we did. So that's kind of what I wanted to show you. So I wanted to show you that we need to be able to assess brain rhythms at various stages, because otherwise we cannot really provide the best care and protect the brain. So brain regions are very important in neurology, especially pediatric neurology. And as I said, the younger the child, the more important for us it is. And what is normal and what is abnormal, I showed you, very much depends on the stage and the context. And in little ones, something that is normal and it's certain age context can be very abnormal in the next. So this is what we do. And that is all.